Okay, class, in this lesson we are going to be learning about simple harmonic motion. So simple harmonic motion is motion that can be modeled by a sine or a cosine function. Some words that we use to describe harmonic motion is when something oscillates or vibrates or rotates. You often see like a spring. If a spring has a weight on it and the spring is going up and down, okay? Or you might have, say, a pendulum that is swinging side to side, side to side. That would be something that can be modeled by a sine or cosine function that oscillates and vibrates and rotates through simple harmonic motion. So some notation and definitions. We have some couple extra letters. We have this letter here. It's a Greek letter omega. It looks like a W. Essentially, it's in the same place as when you have the function y equals a cosine b of t, where b affected the period. It's the same thing, it's just for the applications of simple harmonic motion, your book is using the omega letter, so I'm trying to be consistent with that. A still has to do with amplitude. Instead of a y, it is d for the displacement, or the distance from the origin at time t. Okay, so amplitude is the same. If a is a positive number, then it has positive displacement. If a is less than, then it's negative displacement. So the W-looking character is the Greek letter omega, and it's essentially the same thing as B. Equilibrium is when something is at rest. So if you can imagine a spring with a weight on it, if it's just hanging from the ceiling right here, then we'd say that this is at equilibrium. But if I took the spring and I pulled it down here as far as I could go, since it's below equilibrium, it would be maximum negative displacement. And instead, if I took this weight and pushed it all the way up against the ceiling and held it up here all the way up high, then this weight would be above the equilibrium or above the midline, so it would be at maximum positive displacement. Okay, so equilibrium is just when it is at rest. Okay, if you think of like an old grandfather clock for a pendulum, so you have a pendulum, it's just sitting there. I can take the pendulum and I can pull it back here and then let it go. And then if it's back here and I let it go, then it's going to swing here and then it's going to swing back and forth. But when it's at rest, it's just sitting there. So this is where equilibrium would be. Okay. So A and T are real numbers. It's just A is the amplitude. So it's just going to be some sort of real number, not going to have imaginary T. It has to do with time. The period, it's 2 pi over b, but remember we're using this letter omega to be consistent with our book, but it's still the same thing. And it's the time, the period, it's the time it takes to make one complete cycle. So graphically, you know, one period of cosine would look like this, or one period of sine would look like this. So that's the time it takes for one complete cycle. For a spring or a pendulum, if the pendulum starts here and it's going to swing over here and then it's going to swing back, that's one cycle, that's one period, there and back. A spring that is attached to the ceiling, you pull the spring down and then you let it go, the spring is going to bob up and the spring is going to bob back down. That's one cycle going up and down, so that would be one period. The frequency, which was cut off here, the frequency is omega over 2 pi. It's the reciprocal of the period. It's the number of cycles per time unit, so it's just the reciprocal of the period. Okay, so before we get to this example of a buoy, I do want to show you an example of a spring. Okay, so here's an example of a mass on a spring, and I'm going to pull the mass down. This is as far as it can go, and then I can animate the points and look at the where it goes. So this is its pull down as far down as it can go, and let's just watch the path that it takes. So it's mapping out its distance from the equilibrium. It goes up. This is where it was at rest. The equilibrium, now it's below. See, as time goes on, so as time went on, the spring it started down here, and then it went up, and then down, and then up. Now, the spring wasn't moving to the right, the spring just went up and down. But as time went on, this just shows the motion of the spring being down there, the spring being up there, the spring being back down there, and then it's starting all over again. Okay, so let's go back to the example. So in this example, instead of having the spring, we're having a buoy, and it's oscillating in simple harmonic motion as the wave goes past. So essentially, you have this buoy sitting out in the water. Okay, I'm not an artist, so here's the waves, and then a wave is going to come by, a big wave, which is going to cause the buoy to go up high, and then the wave is going to go past, and then the buoy is going to go back down low again. So if you can imagine, the buoy is here, then the wave's going to go to cause the buoy to come higher up, and then the wave's going to go past, which causes the buoy to go back down again, and then eventually as it calms, the buoy is going to be back here, kind of like if you imagine like a lake that's flat glass. Here it's smooth, and then a big wave comes in, it causes to push the buoy higher up. And then the wave goes by, which causes a little depression before it kind of evens out again, where it's at rest or equilibrium. So the buoy is going up and down, it's bobbing up and down, and it's going in simple harmonic motion, which means it can be modeled by a sine or a cosine wave. At a certain time, a buoy moves a total of 6 feet, so it moves a total of 6 feet from its lowest point to its highest point. Okay, so between its lowest point and its highest point, it's a total of 6 feet. And then returning back to its highest point every 15 seconds. Okay, so what that means is it's at its highest point, it starts from its lowest point to its highest point and back down to its lowest point every 15 seconds. So this every 15 seconds from its lowest to its highest, back returning to its highest point every 15 seconds. So that's going to give us some information about the period. So we're going to write an equation of motion of the buoy if at time t equals 0, it's at its highest point. Okay, so as time goes on, okay, so here is where t equals 0, because we're always going to map the t versus the distance. So at time t equals 0, which means on the y-axis, it's at its highest point. So is it a sine or a cosine function if it starts at its maximum? Well, it's a cosine function, so I know it's going to be d equals some value for a, which we'll talk about, cosine, and then I'm going to find my omega value for the period, t. So I need to find my omega, and I need to find my a value for the amplitude. So if we have our equilibrium up here, and it moves a total 6 feet from its lowest point to its maximum point, from equilibrium to its maximum, it's 3 feet, which tells me that my a value is 3. And it's a positive 3 since it was starting at the positive value. Okay, so if we're going to look at a cosine function that looks like this, it says it takes 15 seconds for it to get this distance. So the period is 15 seconds. Okay, which is 2 pi instead of over b, we're using the letter omega. Feel free to use b. And just solve for omega, or b if you're using b, and you get that it's 2 pi over 15. So I'm going to put that value in here, 2 pi over 15. And we're using t for time instead of x, but you know, it's essentially the same thing. So this right here is our equation of motion describing this buoy. And we're going to find the maximum displacement. So the displacement is how far it goes from equilibrium. So the furthest from equilibrium. Well, it went up to 3 and down to -3. So the furthest it goes from equilibrium is 3 feet. So the max displacement is 3 feet. Yes, sentences, yes, units for sure. So the maximum displacement is 3 feet. How far is the buoy? How far is the buoy from equilibrium after 4 seconds? So this is t equals 4. So we can just plug it into our equation. So we have d is 3 cosine of 2 pi over 15 times 4. The angles and 15ths are not on the calculator, or sorry, not on the unit circle. 2 pi times 4 is 8 pi, so I'm just going to simplify this as to 8 pi over 15. So since it's not a unit circle number, we have to use the calculator. If it was a number on the unit circle, you would use the unit circle, of course. And this angle is a radian, so we're going to be in radian mode. Okay, so we're going to put this into our calculator in radian mode, and you get out 0.3136, I believe. So we're going to answer the question, how far is the buoy from equilibrium? So to answer the question, first note that it's actually a negative 0.3136, sorry about that. So it's negative when you plug it into calculator. So we interpret this negative displacement that it's below equilibrium. If it was a positive number, it would be above equilibrium. So the buoy is 0.3136 below equilibrium. So you should interpret the negative sign as below. If it was positive, you would say above equilibrium. So in your sentence, I'm looking to see that this is here, it's positive because we're saying it's this many feet below equilibrium. So the below is what you use instead of the negative sign. Okay, let's move on to the next problem. So in this problem, we have a pendulum. So we have a pendulum that's going to move from side to side. And here is the equation of motion. What is the maximum displacement of the pendulum? So this is a cosine function. It's a positive cosine function, so I know it looks like this. Since the a value is 3, I know those values are 3. So we can write the sentence to answer the first question. Okay, so the maximum displacement is 3 feet. Since when you graph it, if your midline is your equilibrium, you can go a maximum of 3 feet from it. When it says what's the shortest amount of time in seconds, it will take for the pendulum to reach its original position. Okay, so if this is the motion, we graphed it. We want to know the shortest amount of time it will take for the pendulum to reach its original position. So when it starts, it's up there. Here is the first time it reaches its original position, because remember, as the pendulum swings back and forth, it's going to get back to its original position. So it's going to perhaps start over here, the pendulum, and then it's going to swing over here, and then it's going to swing back here to its original position. And I want to know how long does it take to get back to its original position. And it's going to continue to swing back and forth, which is each time you graph a period. But I want to know the shortest amount of time it will take for the pendulum to return to its original position. So the first time. Okay, so that's the 1 period right there. Well, we can solve for the period, so we can find the period, which is 2 pi over omega, which my omega value is pi over 4, which is 2 pi times 4 over pi. The pi's cancel, 2 times 4 is 8, and we're told in the problem that it's in seconds, so we can answer the question. So when it says what's the shortest amount of time it will take for the pendulum to return to its original position, it takes 8 seconds for the pendulum to return. Okay, the third part, what is the least positive value of t for which d equals 0? So remember, t is my horizontal axis, so what's the smallest t value where d is the y value, equals 0? Well, right here, and here, and here, and here are all the values where d equals 0. So if I want to know the value for the least value, that would be right here. This is the least value for where d equals 0. Well, that's just one of the key points of our graph, so it's the period divided by 4, right? Because your key points were all of those, so if I find my period, divide it by 4, I get 2. So the least positive value for which d equals 0 is 2 seconds. Because it takes 2 seconds for the pendulum to go from here to here, then 2 seconds to get to the next key point, and then 2 more seconds, and then 2 more seconds. That's a total of 8 seconds, 1 period, to make one of these. Okay, so this is where it is at equilibrium. So if you take your pendulum and you model where it's at equilibrium, if it starts here, it's at equilibrium after 2 seconds. Then 2 seconds it's over there. Then 2 seconds it's back at equilibrium. Then 2 seconds it's over there. Okay, so how far is the pendulum after 0.25 seconds? So we're going to plug this in for t into our equation. So I'm going to plug that in now. Okay, so we're going to plug it into our calculator again in radian mode, since this is a radian, and we can answer the question. That is 2.294, and our units is seconds. Sorry, it's distance, and the distance is in millimeters. So let's answer the question. So since it's a positive number, the pendulum is 2.94 millimeters to the right of equilibrium. Right meaning to